going to tell us about abelian reflection arrangements in the guise of a stone.
Thank you very much for this nice introduction, and thank you, of course, to the organizers for inviting me. And you know, I could unfortunately only come rather late, but it still was 3 very exciting days with lots of different things. So I kept thinking, maybe I can try to say at least a little thing for everyone. And let's see. So first of all, I should explain the title, a stepping stone. So my idea is, you know, what are reflection arrangements to arrangement people, if not the like trampoline to get an idea and test a conjecture, then maybe is going to pan out for the general case, right? That is my mantra here, and I want to do it in the following philosophy, in trying to extend our well-known setup of hyperplane arrangements towards some arrangements that are not of hyperplanes. They may be of some kind of hypersurfaces in different ambient spaces, but still where you can control a little bit what goes on. Just a quick reminder for those who just joined the conference 10 minutes ago. So it is an hyperplane, an arrangement of hyperplanes, right? So the setup is some people look at the complement space. It's a manifold, it's a geometric topological object. Some people combinatorially minded say, but this is source of lots of combinatorial goodies, right? And one of the main invariants is this set of intersections. So this is a partially ordered set, and it contains, the elements are all intersections that are generated by the hyperplane. So in this example, all the hyperplane meet at the origin. The origin is the top because I'm ordering it upside down, right? It's reverse inclusion. The origin is the top. You see, I have 5 hyperplanes here, so I have 5 guys here, and this generates 6 lines. These are the 6 points, right? So this is a poset which, on the one side, it's rich by itself in structure. People like to say this is a geometric lattice. Don't be afraid. Geometric lattice means, okay, it's a lattice, right? Joints and meets exist, and all it's chain finite, and also geometric means if I go one up, means I go down one dimension. That can only happen if I'm joining by an atom, meaning cutting by a hyperplane, right? So the only way to go down a dimension is to cut with a hyperplane. So that's a geometric definition of a geometric lattice. These are very rich objects, and they are the entry door to matroid theory, of which we have also heard. So some people like to do that, and some people like to play the one against the other, right? So this poset is interesting, but it also tells us about the complement, vice versa. Okay, can we do that in some kind of more generality? So I don't regard this right-hand side as something different, but you know, I want to do a story that encompasses everything. So the first item here is that somehow you need to modify the definition of what's your combinatorial data. I'll try to give you at least some reason to believe that it's not anymore as smart as before to say the poset of intersections, because some intersections, as you see here, if you intersect the blue and the red guy, they got one intersection, but the intersection is disconnected, consists of 2 points. And the whole story here, these 2 points should be treated separately because, for example, in terms of incidence, they are different. The point in the front is contained in the green guy. The point in the back is not contained in the green guy, right? So I am getting these 2 points as different elements of my poset. That's not my idea. This goes back to at least to Zaslavsky in the 70s when he was first considering these sections of manifolds by submanifolds. It turns out to be a useful thing. And here, however, we don't know what kind of structure does it have. I mean, you can already see it's not a lattice. It's not even a semi-lattice. These 2 guys have 2 minimal upper bounds. Those 2 guys have 2 maximal lower bounds. It's not a lattice, not semi-lattice. But it's not just anything. I will show you some structure is there. For example, we can see that intervals, so if you pick a maximum element and look at everything which is below a maximum element, that's always a geometric lattice because let's say you pick this maximal element here. So what you see below, it's really the intersection poset of the hyperplane arrangement that you see in the tangent space around here. And so intervals are geometric lattices. Beyond that, it's not exactly clear what that is, right? So, and so the question is, what's the generalization of a matroid you should put there? What's the structure of this poset? What's the topology of those complements, right? And do they talk to each other? To what extent the poset and the topology? So, and so the mantra of the talk is, you know, can I say something? Can I say maybe just make a, what do you say, a humble suggestion, a modest suggestion based on what happens in the Coxeter case? So my program is, the topology should tell you exactly what kinds of hypersurface arrangements I want to look at, right? And then I want to say a little bit about what happens poset-wise for Coxeter arrangements and what happens complement-wise for this Coxeter arrangement, and see what happens in general, okay? Good. So if you already want to switch off, that's already not a bad point, right? You already know what I'm going to talk about. So, but for those who are interested, so what kind of arrangements I want to look at? For lack of a better word at this moment, let me call them Abelian arrangements. So this is a story that is going on now for, I want to say, 10 years, more or less. So here is the one picture snapshot. Here are three integer vectors, elements of a free abelian groups. Okay. Now, on the left, I interpret them as linear forms in a two-dimensional vector space. This defines an arrangement, right? On the right-hand side, I interpret them as characters of a torus, and the kernels of these characters define that arrangement I was giving you before, okay? So the story is you fix some elements in a free abelian group of a finite rank, right? And then also you choose your favorite ambient space, and this gives you an arrangement. Slightly more precisely, what kind of ambient space do I want? Well, for today, I want to focus on connected abelian regroups. So I will write this strange G here to mean some power of R times some power of the circle, right? So here is, of course, the case G equal R, because, you know, what I'm going to do with this, right? Is, well, I'm going to fix my, this is not very predictable. So I'm fixing these integer vectors, right? These are my integer vectors here. Let's say for today, it's a full rank, non-zero to make things simple. And then this define an arrangement because each such vector defines such a homomorphism from here by evaluating an homomorphism here at my vector. I get this morphism, and the kernel of one of these guys is some kind of hypersurface. Okay, it sits inside G to the D, so it's G, and the power is the rank of my lattice. Okay, here I have G equal R, D equal 2 because this is in Z2. I get an arrangement in R2. Right? Here I have G equal S1, D is equal to 2. I get an arrangement is S1 square, which is the only two things I can picture, right? From a topological, at least, point of view, these are three interesting cases. Of course, when G is equal C, I get complex hyperplane arrangements. Okay, rational complexified hyperplane arrangements. What people call toric arrangements is when G is C star. So I get an arrangement in a product of copies of C star, and C star as a group is like R times S1, right? So it's the case P equal 1, Q equal to 1. So Q here is not, there are no Q analogs. I'm deeply sorry for this. So so we talk about elliptic arrangements when G is S1 times S1. As a group, it is related to the idea of an elliptic curve. Topologically, this is very different because it is compact, right? And the others are not. So this idea of kind of parameterizing these arrangements via P and Q, I got from a paper of Masahiko, Tan, and Liu. Sometimes we call them PQ arrangements. Anyway, this is the kind of stuff that's going on. The definition may be a little bit unfriendly to absorb, but if you are like me, you just really only keep in mind this, okay? The picture, so that works. So you see, these are some hypersurface arrangements, but not just anything, right? There is some algebra still involved in the definition, and let's see whether we can say something of this. So I had claimed that my poset of connected components of intersections seems to be a right tool. I don't have the time to do the full story. Let me just give a couple of snapshots. For example, the characteristic polynomial of this poset, as defined, for example, in Galen's talk, right? That's a theorem, also the same paper by Masahiko and his co-authors. If you evaluate this, you know, at a smart place, you get the Euler characteristic of the complement, and that's general, right? Other things, for the moment, we only know in some cases. For example, if you want the cohomology of the complement, of course, classically in the arrangement case, this is the Orlik-Solomon algebra, right? We heard repeatedly about, and it is, you know, as a ring in terms of the poset, right? For the case of toric arrangements, arrangement C star to the D, so the poset, with the poset, you can write down the integer cohomology groups because they are free of torsion. So you can compute the ranks via the poset. You can write down the ring structure over Q, but the poset does not determine the ring, the cup product with integer coefficient. So this will be a little bit the theme, right? Some things just go over and some other things just get a little bit more interesting, right? So, but that's the only two cases where at least I know any descriptions. The elliptic case is really very different. The elliptic case will have torsion. So it's a whole other story. But at least this is, you know, there are other things. You can look at wonderful models, not only for the linear case, but for the toric one also. Poincare polynomial. Anyway, this guy is the right tool to look at. So at least I made a little bit of advertisement. My poset of connected components may be worth a look. Okay, so these are the arrangements. So what's a Coxeter arrangement in this case? Well, you know, just take, you know, for your integer vector, take roots of, let's say, a Weil system, okay? How bad can it be? So here is, you know, B2, for example, right? For G equal R, that's the familiar guy. For G equal S1, it's this, okay? So what do we know about the poset or the complement in these cases? So first of all, Christian Bibi wrote a paper where in this case, the poset, we can write down explicitly, it's a poset of certain partitions with decorations. So you can actually say what it is, right? Analogously as what we know in the linear cases, right? So, and using this, you can go and ask questions, try to find answers. So for example, you can go and see, well, in both linear toric elliptic cases, this is actually an EL shellable poset. You don't need to know what that means. If you know, very good. If you don't know, there is no harm in it. Just know that in the case of hyperplanes, so geometric lattices are always EL shellable for every hyperplane arrangement, and even beyond that. More than that, EL shellability is actually a way to characterize geometric lattice. You can define a geometric lattice in terms of shellability properties. So that's interesting, right? These guys are still shellable in the Coxeter case, yes.
When you say that it works for ABCD, does it mean that it doesn't work for the other types, or we're not sure how to move?
It means that that these exist for those four types, and so therefore, you know. So, so that's something. If you compute the characteristic polynomial in the linear and the toric case, it factors. In the linear case, we know, and we know at least 10 reasons why, right? In the toric case, it factors, that's a paper by Federico Ardila, Castillo, and Henry. It factors, of course, I'm not writing it factors in linear factors, right? Because that's not true for the dn toric case. The dn toric case factors, but it has a quadratic factor somewhere, okay? But still, something is happening. And of course, mentioned yesterday, this, of course, linear finite reflection arrangements are k-pi1, so the complement is aspherical, right? That's true in the toric case too. Why is that true? Well, we have heard of this yesterday, of this recent result, right? That affine reflection group arrangements are k-pi1 by work of Paolini and Salvetti. And if you think about it, you can, you know, on top of every such toric arrangement, you can lift to one of these, you know, periodic Euclidean Coxeter group arrangements, right? So on the complement, this is a covering. And so if this guy is k-pi1, that guy is 2. Right? So we know these are k-pi1s, the Coxeter case by Paolini and Salvetti. And so these guys are k-pi1 also in the toric case. So that's about all that I know, except that I was forgetting. Now that we have this idea that we want to study maybe this arrangement in terms of what happens in the lifting to the universal cover of the torus, well, it is also true, I can also write this poset as the poset of intersections of this guy, quotient by ZDN. That's poset quotient, right? It's I'll talk a little bit about that. So this is a little survey on Coxeter Abelian arrangements, as far as I know. Everything else you will have to prove yourself. And in some way, right, I want to go and talk in the next moments about 2 things, right? First of all, on the poset level, right? What can I say about shellability? What does this thing give me, right? And on the k-pi1 property, you know, as a token of 2 things, right? So everything, so several things work well in this Coxeter case. What among these things is a little signal of a general statement? Okay. So that's the second point where you can just stop listening, right? So this is the Coxeter thing. So now the next 2 points are, okay, this is good. So how much of this can I prove in general, right? Yes.
It's possible to generalize for high genus curves.
Well, if you can define, yeah, I don't know. I have not looked at this. You can do product of S1s as much as you can. You can do high genus curves. You have to have a way to define your favorite hyper general surface. I mean, maybe I can answer at the end of the talk. This, I'm not sure. I never looked at this, and now I'm thinking how you would go about this. But maybe I should not do it like loudly now and with cameras rolling. So maybe in the question time afterwards. Okay. Thank you for the question. Okay. So the first thing I wanted to say is, okay, this shellable thing. Okay. Shellability is something, you know, very, very strong combinatorial property. What happens in general? Here, a little aside, so there is something called the Cohen-Macaulay property for posets and simplicial complexes. We have already heard it, just a little reminder. So if P is a poset, I can look at the order complex of this poset. This has 1 simplex for every chain in the poset. You see, this little poset has 3 element chains. So this simplicial complex has 3 triangles, right? So the notion of a link of a simplex is I fix my simplex sigma, and I look at all the cells that appear in some of the simplices that contain my sigma. So that's your example here, that sigma, that's the link of sigma. I call this poset Cohen-Macaulay if some homological condition holds for every link. I want a cyclicity up to possibly the last dimension, right? Of course, this depends on the characteristic of the coefficients field that I get, right? So there is a notion of Cohen-Macaulay in characteristic kappa that is there. And the only thing important for this talk is that every shellable guy is also Cohen-Macaulay for every kappa, okay? And so if you were, for example, to find an example of a toric arrangement where the set is not Cohen-Macaulay in some characteristic, you already would know that this guy cannot be shellable. So bummer, okay? These guys, so the Coxeter guys are shellable. The general things are not shellable. Well, let's go home. Maybe not, okay? So we have an example, a toric arrangement, dimension 3, 4 hypertori, not Cohen-Macaulay, kappa equal 5. Can we understand this? Can we understand what's going on? And here is maybe my main point of that talk. So it really pays off to consider, I want to go back to this idea that a toric arrangement or whatever of these Abelian guys is covered by a periodic arrangement, okay? So this is my take-home slide, if you want. So consider any one of these Abelian arrangements. I lift it to the universal cover of the ambient space. What do I get? I get a periodic subspace arrangement, periodic affine subspace arrangement. This is not just any old subspace arrangement. It's a very nice subspace arrangement. For example, the poset of intersections is what we call a geometric semilattice, which is something, right? It's not a geometric lattice, but the name says it, it's almost as nice, right? So it's a strongly structured poset. And so I may want to study the action of this group of translations on this poset, okay? So the idea and what I found useful is to say, okay, maybe instead to do, axiomatic matroid theory, I want to axiomatize group actions on these guys, on these matroidal things, right? And if I extract the right definition, I can prove things abstractly. So examples of two properties that you may want to take as definitions or axioms. First of all, let's not yet look at this. So first of all, what happens if I translate an affine subspace? Two things can happen. I either translate it inside itself, so the guy remains fixed, right? Or I translate it and I get something disjoint. Okay, now let us reverse this implication. If I am translating this guy and it meets the original guy, then it must have remained fixed, right? If I translate, right? So that's what it is. If any x gets translated to gx and they have a join, then they must be, then G stabilizes X. And this is a single simple thing. I call such actions of any group on a coset translative because the idea is of translations, right? So this is a very basic thing. And I'll need one more. Look at stabilizers in the subspace case, right? What's a stabilizer of subspace? Well, it's a direct summand of Z to the D, right? Of prescribed rank because, dimension of this thing. So the stabilizers have certain Z to the something, prescribed rank that goes up, regularly, direct summand of G, okay? Let's play this game. So it turns out that this is a game of high reward, okay? One story I'm not going into is the following, is the matroid story. So if I take any finite height geometric semilattice, remember those posets, right, of the periodic arrangement, they are posets, they are finite height. They may be infinite like that, right? But they are finite height. So any group acts by automorphisms. So I can build this quotient that's just the set, the poset of all orbits ordered so that, ordered by comparability of representatives, okay? And if you want to go the matroid story, this is already very rich. For these things, you have deletion, contraction, recursions. You recover G-tat polynomials. You recover arithmetic tat polynomials. You recover arithmetic matroids, even in more generality. There is a nice theory of invariants of standardized rings. You can do the standardized ring of the infinite thing, the group acts, the invariant ring as interesting H polynomial related to the characteristic polynomial. Anyway, this is a very nice story. You see, I'm really tempted to tell you, but don't have the time. I only have the time for one sample theorem, this guy. So if the action is refines, that's the condition on stabilizers I was mentioning before, then the quotient is Cohen-Macaulay in almost every characteristic. It's Cohen-Macaulay in all characteristics except those that divide some number. So you have a group action, you look at stabilizers, you don't really want to know, I can tell you afterwards, right? But you can look at this, you compute, it's a number, it's delta. And the theorem says the guy is Cohen-Macaulay is always except in characteristic that divide this delta. Unsurprisingly, our non-example has delta equal 5, but the theorem is not always optimal. Okay, so this is, and of course applies to all abelian arrangements. Why? Because I designed these conditions inspired from the realizable case. Okay, so my first upshot here is that, this poset story has to do with group actions on geometric posets. Okay, and I think this is, the more I look at these things, the more subtle things appear. But I would like to move on. This was my token of the poset thing, right? For example, we took the shellability thing. They are not shellable, but that's not really a bummer. Somehow a more refined structure appears, right? A more differentiated thing. So you could argue it's interesting. Now, some of you don't care about posets or algebraic combinatorics or maybe matroids at all. So for you, I'm not now going to talk maybe 10 minutes about topology of the complement, right? So what was the thing that was true for Coxeter linear and toric arrangements? K/1, right? So you can wake up again if you so feel inclined. Let's start fresh with the K/1 problem. We heard a whole talk yesterday about the K/1 problem. In general, right, one of these arrangements is K/1 if it doesn't have any non-trivial higher homotopy group. And the old problem is, can I detect this by looking at the poset? This is, of course, wide open even for hyperplanes. So since I can't do it for hyperplanes, I try to do it for more difficult stuff. So that's a sound principle. So we have heard yesterday that for linear, in this case, only covers the finite, right, case arrangements. So linear simplicial arrangements are K/1 by the famous theorem by Delucchi. Euclidean Coxeter are K/1, and as I explained, therefore toric Coxeter are K/1. That's part of the story. That's wonderful, but that's technically not in terms of the poset, right? This is, you have to look at the group, you have to look at dual structures or whatever. There is another class of arrangements that are, known to be K/1, detectable from the poset. These are called fiber type arrangements. Terao, Folk, and Randell in the 80s set up this machine. And somehow we were tempted to say, okay, what happens beyond linear, right? Can we study fiber type abelian arrangement? Is this a combinatorial notion, right? Fibrations will not be linear anymore, but let's see. Okay. So I have 2 more slides, right? 2.5 more slides. One is what's a fiber type arrangement in this generalized setting. The other slide is how can I detect it combinatorial, okay? And then there's one special mention for Alex Sucho. So what's a fiber type abelian arrangement? I don't know if you should really read this thing, but so the idea, so from very far away, the idea I call an arrangement fiber type if the complement sits atop a series of fibrations, and there are smaller and smaller arrangements, and the thing fibers recursively. Now, in the linear world, everything is linear. In the non-linear world, you have to just do something. So fiber type, if either it's got rank 1, or I can split my integer lattice, okay? So, you know, a split direct summand of rank 1 so that the new ambient space has rank 1 less, right? And the induced arrangement downstairs is again, that's a recursive definition. It's again fiber type will, you know, let's say. And this natural projection from G to the D to G to the D minus 1 induces a fibration of complements. You don't only want the fibration, you want to control the fiber. So I want to pass from 2-dimensional torus to 1-dimensional torus, okay? So that it's a fibration, right? And the fiber, as you see in this case, it's NS1 minus a bunch of points. Okay. In general, it's G minus a bunch of points. Once again, I have a big arrangement. I don't know what it is. I have downstairs 1 rank less, some kind of smaller arrangement. Okay, that's my B and that's my A, highly symbolic. So, and I want that if I go from here to there, I am fibering the complement, and the fiber is a punctured version of G. This we can characterize. Now, what does it have to do with K-pi1 property? Well, you got a sequence of fibrations, right? And every step you can do long homotopy exact sequence. And but you need this fiber to be very nice for this sequence to just split. And so you need, so this only gives K-pi1 in the cases where this is particularly nice. And fortunately, in the linear toric and elliptic case, this is because if I puncture C or C star or S1 times S1, I get a wedge of circles. It's, you know, and then it's yes.
I was just wondering, in the compact case, is it split your vibration?
Oh, let me get back to that. I have that's a 0.5 slide. Yes. Okay, but that's the notion of vibration. Whatever it is, gives me K-pi1. And now, since I thought I should at least tell you one thing, like so the next slide is for those for the connoisseurs, like for the connoisseurs. So how do I detect this on the poset? Okay, so how do I call super solvable one of these guys that's not even a semi-lattice? Okay, I've got my P, it's finite length, possibly infinite. It's bounded below, and now it's not a lattice or a semi-lattice. So I need to deal with sets of joints and meets, right? Because maybe it's not unique, right? And so I want to define an M ideal. The M ideal sitting inside the big poset. The big poset is the upstairs arrangement, and this inside poset is the small arrangement. Okay, so that's an ideal, means it's down closed, should be pure, all chains have the same length, join closed. If I intersect 2 guys here, they intersect here, or they never intersect, right? First of all, if I take any guy in Q and some atom not in Q, I have to get some intersection. What does it mean? I take any intersection here, downstairs, you know, I'm fibering down. So, for example, this intersection really, you know, is part of the intersection of 2 hypersurfaces in the big arrangement. And so the atoms that are not in Q are what Terao calls horizontal things. So they are, as horizontal things are, like this. Right? So an intersection here is really product with something that meets any atom not in Q. Okay, that's the first thing. And also every maximal element of P sits atop a maximal element of Q, which is modular in this. Remember, this is a geometric lattice. Here I can take the usual modular definition for geometric lattices, which is expressed in terms of rank, if you want to, whatever, you know, this is what it is. Now, if the P poset is a lattice, this is exactly the old definition. So an M ideal in a lattice is just a principal ideal generated by a modular element in the old-fashioned way, right? Of course, I call the poset supersolvable if I can find a chain of such ideals that go down the length one by one. So I need one more little thing, which is maybe I want to be really, really special and not only require some intersection, but exactly one intersection for some reason, right? This I call strictly supersolvable. So the general mantra is that supersolvable classifies the vibration thing, and the strict supersolvable case gives you lots of combinatorial goodies. So this is the theorem, fiber type, equivalent to this supersolvable for the poset, okay? And therefore supersolvable combinatorial elliptic arrangements are K by 1. Okay. But now there are many other things, enumerative and so on, that we want to have. So if you are strictly supersolvable, then you have your usual factorization, for example, of the characteristic polynomial. You can control monodromy is the non-compact case. In the strict case, so this is always a vibration, it has some monodromy, but if the thing is strictly supersolvable, this monodromy is always trivial. By the way, this is always pulled back from the Fadel-Neuwirth configuration space thing, right? And so on and so on. There is an LCS formula for the toric case, right? And so on and so on and so on. But my time is getting close to disappearing. So I hope at least I gave some idea that some of the known things work in a far more interesting way. Not that they are not interesting before, like this I have not claimed, but more interesting way in this generalized setting. And somehow some things, you know, some evaluations of these polynomials that usually is boring, characteristic polynomial at 0, I think, right? It's boring. But that now in general is not boring in the toric elliptic case because it counts something, right? So something which is always 0 or 1 in the, probably 1 in the whatever. Yeah. Anyway, yes. So poset, you should look at group actions. I think there's a theory, a metroidal theory to be there. And for the complement, we have some combinatorial models for toric and elliptic, and you have, for example, this supersolvability story that seems interesting. So that's my closing thing. So summarizing slightly, so there's the poset story, and I think there is some kind of equivariant matrix theory where the case of the trivial group gives you just a plain old matrix theory. If the group is Z to the D and you impose some conditions, you get arithmetic matroids, and so on and so on. I mean, there are, of course, I still don't know exactly what the right kind of group actions is. I'm just stumbling and seeing what works in the hope that at some point something will crystallize. I think the interesting thing is, you know, can I, you know, as people study in geometric group theory, right? You have the quotient, or you have a poset in this case. Can you tell me when this is a quotient by this kind of group action? And that would help a lot, because I didn't tell you because I don't know an axiomatic definition of this guy. I only know, for me, the definition is geometric semilattice with group action translated. In this case, of course, the homology thing already is not a lot. And somehow I feel I should say the word freeness, right? So, but I don't know anything about freeness. However, I mean, these guys, these strictly supersolvable guys, the polynomial factors. And this means for example, in the toric case, also it's the Poincaré factors. And maybe, I mean, the toric case seems to be the tamest thing after the linear case. I know in principle, this modulus of derivation theory can be formulated for beyond the linear case. And I wonder whether this may be a first test case, maybe strictly supersolvable toric arrangement to see what works in the nonlinear cases. But that's something you will have to teach. Thank you very much.